So today we have not one speaker, we have two speakers, so this is very good. So maybe the student can ask for 2 certificates instead of 1. It's possible. In any case, we have 2 speakers. One is Rui Silva. Rui Silva made his PhD at the Universidad Autónoma in the group of Fernando Martín. And if I understood correctly, he worked on quantum dynamical simulation of a system in presence of strong electric fields. And then after that, he moved as a postdoc to the Max Born Institute in Berlin, where he started working in high harmonic generation in solids. Okay. After that, he moved back to the Universidad Autónoma, now to the group of Johannes Feist, when he worked in ultra-fast dynamics of polaronic system. And good for us, in 2021, he came to this institute, and he continues working with us. He has some CAISA grant, and he expects to be in the near future to funcionario, so he's a good person. So, on the other hand, Álvaro has a similar or parallel career. He makes also his PhD in the Universidad Autónoma in the group of Fernando Martín. And his thesis was in the case of larger field induced dynamics, ultrafast, attosecond dynamics of electrons in atomic system, something like that. Then after it moves again also to the Max Born Institute in Berlin, and also he was working in nonlinear, laser-induced nonlinear effect in, I don't know if it's in solids or molecules, probably you know, but, and then it's very interesting because after Berlin, he moved to Canada, where he make experiments in high harmonic generation in systems. So he's a theoretical and experimentalist. And also, the more interesting thing, the more important thing is I learned today that he has obtained the Ramon Ricajal Fellowship yesterday or today, so congratulations. This is very important. In any case, they both work in the institute in the group of dynamics of electron, and I think that they also like to give talks both together. So there's something like the duodynamic of the attosecond in the institute. So, yeah, you are.
Thanks a lot for the presentation, Luis. So today I'm going to talk about strong field physics in solids from a Wannier perspective, and as Luis told us, this is going to be a shared talk between myself and Álvaro. And perhaps like the first thing is to actually give a special mention to Álvaro. I've been collaborating with Álvaro since almost a decade ago. We didn't collaborate actually at the PhD. We started our collaboration as in the postdoc, and it's really a clear example where symbiosis is much better than competition. And I think that we make a good team in attosecond physics in solids. So I want to start to talk about like nonlinear optics. So when you shine a laser with a given frequency to a target, either it is a solid, a gas, or a molecule, if you shine with a frequency omega, if the intensity of the field is strong enough, then you start to see things that are beyond linear response. So you can start to see things, for example, second harmonic generation, so generation of a photon that is twice the energy of the frequency photon, or further harmonic generation. Usually, these processes are thought within the framework of nonlinear optics, and the framework of nonlinear optics is usually a perturbative framework, in which you basically expand your polarization of your material into a Taylor series with respect to the electric field. And then what you observe is that the intensity of the nth harmonic scales with the intensity to the power of n. So the intensity of the field to the power of n. So in order to observe high harmonics, we are going to focus a lot on high harmonics. your intensity, the intensity of your field must be very, very high. And this is actually a calculated spectrum of high harmonic generation. This was done in my PhD. This is for H2 plus molecule. And what you observe is that when you calculate the radiation of the radiation generated by an atom or a molecule or a solid in the presence of a very, very strong laser field, you observe that you start to see like an exponential decay for the first harmonics. And then what you see is that at some point, you see that the intensity of the harmonics remains almost constant. And this is an indication that our perturbative expansion fails. So if the intensity of the process of nth order is almost the same as the process of n+2 order, then this perturbative expansion is failing. So what you are actually seeing is strong non-linearities that go beyond perturbation theory. Okay. And the process of high harmonic generation, in which you see a huge amount of harmonics that go way beyond the first harmonics, was explained first by, or was not first, but it was really explained, and the insights are coming from this paper, this seminal paper by Paul Corkum in 1993, that gives us a semi-classical explanation of this process. So imagine that you have an atom. Here you have the atom. The electron is bounded, and you have a strong laser field here depicted as the green curve. When the electric field is maximum, this what it does is to tilt the atomic potential, and then the electron is free or can tunnel out of the barrier of the atomic well. Once it's free by this tunneling ionization, then it can accelerate. It's like a free particle. It can accelerate with the field. It goes, of course, it goes away from the atom, but then when the electric field turns its sign, it can come back, and in this coming back can recollide with the parent ion, and in this recollision, all the kinetic energy plus the ionization potential of the atom, all this energy is released into a very, very high energetic photon, and this is the process of high harmonic generation. So not only we generate very energetic photons, we also generate this in a subcycle, so this is a very short instant of time. So it's not only a very energetic photon, it is going also to be a very short burst of light. So these are the origin of the attosecond pulses, and this was the reason why Pierre Agostini, Ferenc Krause, and Wannier were awarded the 2023 Nobel Prize in Physics. So at the beginning, what people were doing, actually before understanding this in a semi-classical way, was to solve the time-independent Schrödinger equation for an atom in the presence of a very, very strong laser field. And what people observe is that when you plot the wave function as a function of time, okay, you see that initially, so this is like time, this axis is time, this is position. So initially your atom is bounded, so you see the electron is really bounded to the atom. And then once you have very high intensities of the field, you see that these bursts of electron wave packets, so these are actually electrons getting ionized by the laser field. And what people observe is that there are some electron trajectories that you can see that they go and they come back. And these are the recollisions. So actually, these numerical calculations don't give you immediately the semi-classical picture, but looking at this, you can start to think that perhaps there is a semi-classical way to understand this, because you actually see the trajectories. And this is the thing that I want to keep you in mind, is that this real space, real-time picture was essential for the development of attosecond physics in atoms and in molecules, okay? Then, so attosecond high harmonic generation was discovered in late 80s. It was only 20 years after that we first observed harmonic generation in bulk solids. This was observed in zinc oxide, and the good thing about this is that now all the things that we learned in the first 2 decades of attosecond science in atoms and molecules to observe these ultra-fast processes in atoms and in molecules can now, all this toolbox of attosecond physics can now be used in bulk solids. And then people start to think about what can we do. Like a solid is much richer than an atom. So people start to look at strongly correlated systems, topological, electronics, excitons, and phase transitions. So this opened really the window. So this discovery of harmonic generation in solids opened the window to explore solid-state phenomena within these timescales. Okay. So imagine that what I want to give you now is a brief cartoon of how harmonic generation works in a solid. So let's imagine that we have a two-band solid. Okay, so you have a conduction band, valence band, and the valence band is completely filled at the beginning, and then you shine with a laser with the frequency of the laser to be much smaller than the gap. Okay, when you have the maximums of the laser field, what will happen is that you have tunneling. So you have some Landau-Zener transitions that promote an electron from the valence band to the conduction band. What is going to happen after is that once you have the electron-hole pair, then they are free to move within the band by the semi-classical equations of motion with in a band. No? So this is just the velocity of a Bloch electron, this has this term that is the band dispersion and this anomalous velocity. And since you are propagating electrons and holes in non-parabolic bands, you will have nonlinearities, and this will give rise to intraband harmonics. Furthermore, we also have another process that is the process in which the electron and the hole, they travel and they can recombine. And in this recombination, what is going to happen is something similar to harmonic generation in atoms, is that all this energy of the electron-hole pair will be released into a very high energetic photon. Okay. So today what I'm going to talk is about how to go beyond this simple two-band model. Okay. So actually, real materials, they have way more than 2 bands. So this is, for example, rhenium disulfide. We have done some calculation. Why the frequency? It's just because of the periodicity of the field. Yeah, in this picture, no, but I mean, this picture would just be a subcycle. So when you sum all of them, then it's quantized. It's just because of the periodicity. I can actually, this is really interesting. So I can really show here. So you see here, like the wave packets, they are very broad at the beginning because you have only 1 or 2 subcycles, 2 cycles of ionization. Once you have more and more, then you start to see, so this would be translated into the energy of the electron, not into the energy of the photon, but it's also, it can be the same. And then once all the trajectories interfere, they will give rise to quantized electronic, here, kinetic energy of the electron. Okay. So this is just like piling up several cycles. If I would have like a very short pulse, then the harmonics are not quantized or are very broad. So today what I'm going to talk, so real materials, they actually have more than 2 bands. So this is rhenium disulfide, so this has nothing to do with this, no? Like, this is not 2 bands. So what can we do to solve actually these things? So before the Joule, so before arriving to articles in which you explore the full complexities of these things, we need to dig. And this is what I'm going to explain today. Now, is the digging, okay, the digging process that you need to do. This is not the picture that I wanted to show. It was an error. So what I'm going to show you is actually how to do numerics of strong field physics in solids. And the articles are these two. The first one was in 2019, and then we just give another twist to the method, and we arrived to this archive that is now in review. And these are the authors of, the co-authors of all these papers: Eduardo Molinero, who was my first PhD student, a brilliant PhD student; Bruno, who is a very good friend and collaborator in Portugal; Misha Ivanov, Fernando Martin, Graham, Giovanni, João Viana, Álvaro, of course, and also Pablo San Jose. So imagine that you have a real material, you want to do electron dynamics in that real material. Like the first thing that can come to your mind is to do TDDFT. So you have some band structure, you want to evolve the electron dynamics in this material, so you can go with TDDFT. The problem is that, I mean, it's very costly, and to introduce effects that are crucial to understand high harmonic generation is very hard, actually. So the other approach is to solve the semiconductor Bloch equations that are the same as the equation of motion for the reduced density matrix. And you can do this in three ways. You can do in the velocity gauge. It has the disadvantage that you need a lot of bands to get the converged results, so we just don't do in this velocity gauge. And then you have the length gauge and the Houston gauge that are almost the same, but both of these approaches have one problem, and is this Barry connection here. So this Barry connection involves derivatives of the bands as a function of k. And so to have derivatives of something, you need to have at least a continuous or function. And as I'm going to show it to you, you have some gauge freedom to choose this. And when you go to very complex materials, it's almost impossible to smooth out all the phases of the Bloch functions. So we have this gauge freedom, and then to choose the phase, or to fix the phase for each Bloch state along the brilliant zone is very problematic. So, but what is actually the origin of the problem? So the origin of the problem is actually this position operator. When you have light at first order, or in dipole approximation, the interaction term that appears has the position operator. And the position operator in a periodic boundary condition solid is ill-defined. It's very easy to understand this because you just have a ring. You have here x equals to 0, here x equals to a. What is the displacement between the first and the second side is a. You go around, and what happens here, for example? What is the displacement? You cannot just assign x and do x of the last one and minus x1, the first one, because it will give you a discontinuity in the position operator. Okay, so the solution is actually to go to the thermodynamic limit, and it's there that appears these Barry connections. Okay, so when you go to the thermodynamic limit, the position operator just becomes like a derivative in k plus this Barry connection. This Barry connection has these derivatives in k. Okay. So imagine that you want to do really a real material. Okay. So in a real material, you go with a DFT calculation with a k mesh, 15, 15, 15. The problem is that, first of all, this is too coarse for strong field physics. We need much coarser grids in strong field physics. And also, the thing that it comes out from a DFT calculation, the phase of the Kohn-Sham eigenstates is completely arbitrary. So how can we go around this problem? Okay, so the problem is really on this wave function gauge freedom, and we can imagine that you have this material. We can try to create a smooth and periodic gauge, but this is a mess. This is a spaghetti. Try to fix the phase of each band with all the crossings in a 2D or a 3D brilliant zone. So this is really, really hard. So the thing that we can realize is that all problems arise when we diagonalize h of k. But we don't need to diagonalize h of k. We can just construct a diabatic basis. So this is what people do in molecular dynamics. So in molecular dynamics, they usually have, they sometimes have this problem of avoided crossings, or in which the non-adiabatic couplings, they diverge. So in order to do, for example, nuclear wave packet dynamics, so imagine that this is like the ground state, this is the excited state of the molecule. You want to do like some nuclear wave packets. When the nuclear wave packet arrives to the avoided crossing, then the non-adiabatic couplings, they diverge, and numerical propagation, if you want to do in the adiabatic basis, is a mess. So what you do is, instead of working with the ground state and the excited state, you just work with the B state that has like a smooth character, and the A state. So this is what people do in molecular physics. In solid state, we have something that is similar, and it is the Wannier functions. So for a single band, what we can have, a Wannier function is really easy to define. It's just the Fourier transform of the Bloch functions. But of course, since I have freedom in this guy, in the Bloch function, the Wannier function is not uniquely defined. So how can we uniquely define? This is like the Wannier community that developed this. So we can change the phase of the Bloch function in order to minimize the spread. If you have a lot of bands, what you do is you just have, instead of minimizing the spread by changing the phase of a single band, you minimize this unitary. You minimize the spread by changing this unitary transformation. Okay, and then you arrive to the Wannier functions. So, and this has the advantage that then you can do Wannier interpolation. So imagine that you do a DFT calculation in a very coarse grid. You construct your Wannier functions, okay, and then when you have your Wannier functions and all the parameters of the Hamiltonian in the Wannier basis, then you can interpolate back into K and calculate in a much finer grid. Okay. So this is just an example. Imagine that you do a Wannier DFT calculation in this. So in this path, I only have 5 points. Okay. So actually, you cannot see bands here. Once you do Wannierization, and you then interpolate into this path, then you have this. So this is really like it is showing you the power of Wannierization. Okay. So the idea then, to our case, is really what we will do is we will do a DFT calculation, then we will construct this Wannierization, and then all the things that were included were encoded in the Berry connections in the Hamiltonians as a function of K, now are encoded in these two matrix elements that are matrix elements between Wannier functions. So they decay exponentially. So when you do the Fourier transform of these, that are now the Berry connections in the Wannier basis, in the Wannier-Bloch basis, they will be smooth. Since these guys decay exponentially, a Fourier transform of a function that is very localized is going to be very smooth in K. And then you can solve your equations of motion in K much easier, because now this object doesn't have all these discontinuities. Okay. So we can give a twist now, and the twist is the following. I show you that this real-time, real-space interpretation in atomic and molecular physics was essential to understand high harmonic generation. But there is a problem. So in atomic and molecular HAG, we have that at all our intuition, all our models, all our calculations were done in a real space framework. When we go to K, suddenly we understand things in the band picture. We have our numerical methods in the framework of K space. So then it becomes two fields that are artificially separated by this river. So because like real space or atomic and molecular physics, HAG is with a real space framework, and then we have a real reciprocal space for understanding solids. So what we actually need is a numerical method that is capable of bridging the two roles. And these are the semiconductor Wannier equations that we formulated in the last 2 years. So what are the problems with K-space approach? So first of all, we have the ill-defined position operator. Then we also need to deal with this artificial discretization of rho. K is not always a good quantum number. So you can have a solid and an amorphous solid. So why you are like fixing everything to a K-space framework, no? And also, like, we need to introduce extremely short dephasing times, and this is a problem that has been around since the beginning of AGG in solids. So what I'm going to show you is that real space is actually the solution of all these problems. What do I mean with real space? So in a crystal, why not to take advantage of the Bloch states, okay? So our dynamical object that we were trying to solve was the coherence between two bands. And what the Bloch theorem says is that these are diagonal in K, okay? Since I have translational invariance. But I know that Bloch states and the position operator, they are problematic. So what we do actually is a very simple thing. It's just we change our dynamical object. Instead of working with K-space states, we just work with these Wannier localized orbitals. And the only thing that we need to realize is that the coherence between this orbital and this orbital is the same as this one and this one. So they do not depend actually on the two arguments, they only depend on the difference between the two arguments, okay? They depend only on the distance. So once you do that, you can really look, for example, at the density matrix in real space. And then you can take advantage of something that is called nearsightedness of electronic method that was introduced by Walter Kohn, that tells you that despite you have a solid state material, your coherences, they die very soon. So if you have a gapped system, for example, like here in HBN, even though your Bloch states are spread all over the space, the coherences between localized orbitals, they die quite fast. This happens the same for metallic systems, but it doesn't decay exponential. As soon as you put some temperature, it decays exponential. And also what this is telling us is that with small supercells that only contain distances up to 50 angstroms, you can correctly describe the physics, because these things decay exponential. So this is log scale. So these things decay really exponential. So with a supercell that can have up to 50 atomic units in distance, you are describing perfectly your system, okay? And then you plug everything, and then you obtain the semiconductor Wannier equations, in which you have now everything written in a real space framework. First of all, this looks much similar to what atomic and molecular physicists are used to. Then we also include these self-energy terms that are essential to describe excitons, and actually are much better to introduce in real space. The Stark shift can easily be dealt with, so this Stark shift can be problematic, but we can take away with a Pearl substitution, and then dephasing can be introduced not only as dephasing between different bands, but we can now see dephasing between localized orbitals. And what we are going to assume is that very far away orbitals, they decohere much faster than close orbitals, okay? So what can we do? We can do, I mean, this is linear absorption. We can do for HBN, MOS2 with 22 bands. We see the excitons. When you see the convergence, you see that the semiconductor Wannier equations, so the real space approach, is much faster in achieving convergence than the K-space approach. And also, when we look at dephasing, so for example here, I'm plotting not populations, I'm plotting coherences between localized orbitals, and you see that when you do the simulation, these coherences behave much like an electron trajectory in an atom. And what you can do is now to introduce some cutoff in order to kill these coherences. This is what we do with real space dephasing, and we are just translating something that we know in atoms. We know in atoms that the long trajectories, they decohere faster. So we are making here this bridge, okay? So this is actually so when you do real space dephasing and dephasing within the bands, we see that they both clean the high harmonics, but there is a good advantage of real space dephasing is that we don't have changes in the low harmonics. So this was actually an artifact of pure dephasing. We can also see the effect of excitons in HHE. So here what we see is an enhancement a little bit near the band gap and near the excitonic peak. So this was a paper by Eduardo. And to conclude, we just seen that perhaps like maximal localized Wannier function is actually the way to solve semiconductor Bloch equations because we avoid this Berry connection problem. And if we go one step further, we actually can get rid of all the K-space picture and do everything in real space. And this is an alternative formalism to semiconductor Bloch equations that provides a natural link to atomic and molecular HHE. And these numerical codes have been used like in more than 20 publications, several theory and experimental collaborations. They are integrated with the FT codes by this Wannierization. So we can use realistic band structures. And now actually this method is being used by several other theoretical groups. So this is our group. Yeah, feel free to talk with us if you want to collaborate. And the second act is Álvaro's turn.
Yeah, so thank you very much for being here, for inviting us. And so these are, now I'm going to focus more about on the results and experimental collaborations that we have obtained with the codes developed by Rui. And so these are essentially our collaborators. Well, yeah, so from the MBI, Olga Smirnova, Misha Ivanov, from the Politecnico di Milano, the group of Giulio Cerullo, in the ICMM, Eduardo and Pablo San Jose, at ICFO, the group of Jens Biegert, and in SLAC, the group of Matthias Kling. So I will talk mostly about the control of electronic and topological properties of 2D materials, which I believe is of interest here. So I will be considering these hexagonal type systems, which have don't have inversion symmetry, meaning so they have two inequivalent atoms in the unit cell. And these include transition metal dichalcogenides like MOS2, MOSE2, and also materials like HBN. And electron dynamics in these 2D materials are governed on the one hand by the usual band velocity coming from the dispersion. And also in materials without this inversion symmetry, the electrons can be driven not only along the direction of the laser field, but also acquire a velocity which is perpendicular to it and which reflects the asymmetry of the lattice. And this perpendicular velocity in momentum space can be included with a pseudomagnetic field, which is the Berry curvature here. So both the dispersion and the Berry curvature govern the electron dynamics in these 2D materials. So if time reversal symmetry is preserved in these materials, then we have these types of band structure with two valleys at K and K prime that are energy degenerate and that have opposite Berry curvatures that go out of plane of the monolayer. So these two valleys carry opposite chirality and they couple differently to external fields. So this leads to optical valley transitions. So in particular, right circularly polarized light couples to the K valley, left circularly polarized light couples only to the K prime valley. And this allows us to create valley polarization in which one of the valleys is much more populated than the other. And this idea launched the field of valleytronics, in which one uses this binary valley degree of freedom as, let's say, an information storage similar to the spin. So we then asked what happens if we drive these type of hexagonal materials with a laser field that has the symmetry of the lattice. Can we control its symmetry properties, and therefore its electronic properties. So this is a bicircular field. It's made by the combination of a circularly polarized omega field and its counter-rotating second harmonic. And it draws this Lissajous figure, so this field as a function of time. And this trefoil field can rotate if we change the time delay between the omega and the two omega pulses. So we applied this type of field to MOS2, calculated via DFT with the codes that Rui described. And in this configuration, we observe valley polarization. Okay, so this valley is more populated, and we drove the system with a field that was way below the band gap and with a high intensity. So we are in the strong field regime. So one can think, okay, yeah, you have valley polarization because essentially you have a circularity of your field. So these are the typical optical valley selection rules. However, if we keep fixed the helicities of both pulses and just change the time delay between the omega and two omega pulses, which we can do with subcycle precision, then we switch the valley polarization, okay? So, conversely, if we switch the switch the helicities of the laser, but keep the orientation of the field relative to the lattice fixed, the valley polarization does not change. So this is not due to the valley selection rules. It is dependent on the orientation of the field relative to the lattice. So what is the physical origin of this effect? Well, we know that during the interaction with this strong field, the electronic Hamiltonian is modified. So this is the basis of Floquet physics, Floquet topological insulators. So we can start from a simple tight binding model of our hexagonal lattice where we have only first neighbor hoppings. And in the presence of the field, these first neighbor hoppings will be modified according to the Peierls substitution, which we can write as a cycle averaged term plus dynamical corrections to this cycle averaged. And then we can ask what is the effect of these time-dependent modifications. So we can do lowest order perturbation theory to see what is the effect of this perturbation. And in particular, these perturbations can induce second neighbor hoppings through virtual first neighbor transitions, just like you have second two photon absorption via virtual processes. So here we can have laser-induced second neighbor hopping. And if we do lowest order perturbation theory, we find that the second neighbor hopping induced by this bicircular field is complex, and the complex phase of this second neighbor hopping depends on the time delay between our omega and two omega fields. That is on the relative orientation of the field relative to the lattice. So what can we achieve with this complex second neighbor hopping? Well, this we know from the work of Haldane. So in his model of a Chern insulator, he showed that the complex second neighbor hopping lifts the degeneracy of the K and K prime valleys, and the sign of this complex second of this complex phase determines which of the valleys has the minimum band gap. So this model was the first example of a topological insulator, but unlikely to be directly physically realizable, as he wrote in the paper. And this is because of the complexity of having this complex second neighbor hopping, in his case by having a staggered magnetic field with the symmetry of the sublattice. But in our case, this complex hopping is not static, but it is dynamically induced by the field. So by tuning the time delay between the omega and the two omega pulses, we can control the complex phase of this second neighbor hopping and therefore control the electronic and the topological properties of our 2D crystal. So here I show a movie in which I will change this time delay between the two pulses. This will rotate the field relative to the lattice, and it will create some effective band structure that the electron feels. And this will be directly mapped onto an observable, which is the populations, the electronic populations in the first Brillouin zone. So as I change the delay, the field rotates the lattice, and this lifts the degeneracy between the valleys. And then electrons are injected, because we are in the strong field process, at the point of minimum band gap. So the valley polarization oscillates as a function of the delay between the omega and the two omega fields, while keeping the helicities of both fields fixed. Okay, so this dynamical modification of the band structure, this is mapped onto this observable, onto the oscillation of the valley polarization as a function of the rotation of the trefoil field. And this is exactly what the experiment in SLAC measured 2 years ago. So they came with bicircular pulse in a monolayer of hexagonal boron nitride, and they could rotate this bicircular field. And then they measured the valley polarization induced by this bicircular field with a time delay linearly polarized probe. In particular, they measured the third harmonic of this linearly polarized probe, just because that is it was background free. Okay, so if the bicircular field induces the same populations in the K and the K prime valley, then the signal measured by the probe is linearly polarized, because we will have the same populations in K and K prime, and this perpendicular velocity will cancel, because K and K prime have opposite vary curvatures, and therefore we will only have a linearly polarized component. However, if we have some valley which is more populated than the other, then this transverse component does not exactly cancel, and therefore we will see an elliptically polarized component of our signal. And the helicity of this elliptically polarized component will depend on which of the valleys is populated. So as a function, what we would expect is that as a function that we rotate the field, we will induce different valley polarizations, and therefore our signal will change from minus to 0 to plus, minus to 0 as we rotate the field. And this is exactly what they measured. So as a function of the trefoil rotation, the valley asymmetry switches from negative to 0 to positive, following the predictions by the theory. And again, I stress that here the two fields are, the helicities of both fields are kept the same, so this is a purely Haldane type process modification. And then the group of Jens Bigert looked at this from a different angle, and they measured it in bulk MOS2. So this material preserves inversion symmetry because it grows as one layer on top of the other, rotated by 180 degrees. This material does not show valley polarization if we drive with a circularly polarized light, because, I mean, we can see that, let's say on the bottom layer, we will have polarization in one valley, and then if we rotate the system completely 180 degrees, then we will essentially have valley polarization in the other valley, so the two effects will cancel. And let's do the same thing now with the bicircular field. So we have one layer, and we know this generates some valley polarization. We completely flip all the systems by 180 degrees, and we have opposite valley polarization. We just have flipped the figure. But note now that the laser is pointing along a different direction. So the laser does not preserve inversion symmetry, right? And this is, of course, not what we have in the experiment, because the layers rotate, but the field does not magically change between one layer and the other, right? So in order to be consistent with the experiment, the field must be exactly the same in both layers. So we have to rotate this layer, and we know this field, and we know that rotating the field by 180 degrees changes the valley polarization. So the result is that in bilayer or bulk systems, the bicircular field induces valley polarization. So this extends, let's say, valleydronics to systems with an arbitrary number of layers. And this is what the group of Jens Bigert, Adikfo, demonstrated. So again, they came with a bicircular trefoil pump on bulk MOS2, which is inversion symmetric, and then they measured the second harmonic of a linearly polarized probe. So since this material is inversion symmetric, we shouldn't expect any second harmonic generation, unless there is some Valley polarization that breaks this inversion symmetry. And this is exactly what they measure. So they measure the strong second harmonic signal coming right after the trefoil pump. And this signal oscillates as a function of the rotation of the trefoil pump, just as in the case of the monolayer. So we are indeed inducing Valley polarization here in bulk also. So, okay, so a major limitation is that these measurements that I have shown you, and essentially all measurements on Valley manipulation, Valley control, do not correspond to real-time Valley switching. So what do I mean by that? I mean that each of these points corresponds to a different experiment. It's just a different time delay between the pulses that can only be made as fast as the electronics in your setup permits, which is, let's say, nanoseconds at very best. So between, and of course, the electron has already decayed again to the ground state. So between one point and the other, we are essentially starting from the ground state every time, not switching, let's say, from one Valley coherently to the other. And so achieving this real-time coherent Valley control is one of the key challenges of Valleytronics. And this brings me to the last part of my talk, which is a recent work that we have done with a group of Giulio Cerulo and in collaboration with Paulo San Jose, so here at ICMM. So now I move to resonant processes again. So we can describe the system just as a V system, one ground state, two excited states, K and K prime, left circularly polarized light, let's say, couples to K, right couples to K prime, and then we have some decoherence processes. So if we come with a linearly polarized pulse, then we induce a superposition of K and K prime, just because linearly polarized pulse is a superposition of right and left. And then we can add a second pulse, which is orthogonal to it. It is phase-locked, and it is delayed by a phase of pi halves. So this is a circular pulse. So of course, a circular pulse will induce some Valley polarization. Now, we delay this second pulse by an integer number of cycles. Do we still get Valley polarization? Well, yes, at a particular frequency, even if we have two linearly polarized pulses separated, as long as the coherence of the system remains between the delay of these two pulses, we will still have essentially a circularly polarized pulse at a particular frequency. So we will still see Valley polarization even if the delay between these two pulses is shorter than the decoherence of the electron hole decoherence. And of course, if we change this time delay just by pi, then we get opposite Valley polarization because the effective field will have the opposite circularity. So as a function of the time delay between the first and the second pulse, the Valley polarization oscillates because we will effectively have a linear pulse, a circular right, circular left, etc. And it will decay, and this decay tells us the information on the exciton coherence time. Okay? So yes, so essentially on the electron hole coherence time. And so what can we do? So in order to achieve this, we need two things. We need that the pulses are short enough so that coherence in the system is maintained. And we need a strong resonant frequency to which the electrons can couple. And so we did this experiment with a group of Giulio Cerulo that managed to have two pulses. So they have this, they call it twins setup. So they have this twin pulses, which they can control the relative polarization between them and the time delay between them with attosecond precision. And so, and after these two pulses, let's say, create some possible Valley polarization, this Valley polarization is measured by, again, a probe pulse, and they measured Faraday rotation. So, so they did this in monolayer WS2, which has a strong A exciton peak, and the bandwidth of these short pulses cover essentially only the A exciton peak. Okay, so so what they observed in the experiment is exactly what we predicted in theory. So this oscillation of the Valley polarization, which persists way longer than the two pulses are overlapping temporally. So this gray curve here is the cross correlation of the two pulses. So you see that the valley polarization persists. And that from the decay of this valley polarization, we can obtain the exciton coherence time, which, since these pulses are so short, we can even measure it at room temperature, and we get a value of 30 femtoseconds exciton coherence time at room temperature. And this is in line with previous experiments that had inferred it from the line widths, so temperature-dependent line widths, or four-wave mixing, although in four-wave mixing experiments, I believe, they could only reach up to 200 Kelvin due to the time resolution. Whoops, no, sorry, I got ahead of. Yeah, so, but one thing is that here, I'm still not showing control of valley polarization in real time, because again, this axis is still the time delay between the two pulses, okay? So this is essentially just like the other experiments, but we could do something on top of this, because they managed in the setup to add a second pair of twin pulses, which they can also control with attosecond precision. So what can we do with this? Well, the first pulse is, so again, first pulse is polarized along x, the second along y, the third along x, the fourth along y. So the first pulse is linear, creates no valley polarization. The second pulse creates essentially a circularly polarized pulse, just as before, and then we get some valley polarization. Then, if the third pulse is chosen as a pi pulse relative to the first, and we maintain coherence, this is just basic coherent control. And so this effect cancels, and we are left with essentially one linearly polarized field. So we kill the valley polarization coherently in real time. And then the fourth pulse, depending on the time delay, can, let's say, switch the valley polarization to the opposite valley or to the same valley or whatever, depending on the coherence. So we can switch on the valley polarization coherently again. So now, this is real time. So this is real time valley switching coherently, on, off, on. And so this is this is in the petahertz regime. So we believe it's the first real time valley switch. So, and this is operating at room temperature. So with this, I would like to wrap up. So I have shown you that a strong field and attosecond physics allows to control the band topology and the valley polarization on a few femtosecond time scales. And thanks to very basic coherent control theory, but really technological jump in attosecond precision, we can now have real-time valley switches. So thank you very much for your attention.
Thank you for both of you. So question? Comment? No question? So I have a question, just a curiosity. Listen, which part of the Brilliant Sun so the electron and the electric field, which part of the brilliant zone is moving around? So it's half of the brilliant zone, a quarter, it's a small.
It depends on the vector potential, so on the intensity and the frequency of the laser. It can cover the full brilliant zone, and actually people have observed Bloch oscillations. And yeah, it can cover the full.
So now the next question is how important is the size of the unit cell in order to observe all these kind of experiments? Because in order to observe just the Stark effect of the oscillation, you need large unit cells to have a small brilliant zone. Do you have something similar here?
No, well, I mean here is here it's just we don't observe any Bloch oscillations or anything like this. So we don't reach in the
electron move coherently along all the brilliant zone.
Yeah.
But with the velocity, which is the derivative of the band structure with respect to k.
Yeah.
So it's not going to take a long time for the electron just without scattering.
So the electron is being accelerated, right, by the field. So just k plus the vector potential plus at. And
I think in some experiments they actually see this. So the electric field is very, very large. So your vector potential really can go up to the edges of the Brillouin zone. And they can see two things. So either the Bloch oscillation, or when the electron goes into the edge of the Brillouin zone, it can jump to another conduction band.
Some kind of thinner tunneling.
Another Landau-Zehnder tunneling. So we have some experiments with Weizmann Institute in which they observe this actually.
So this is one of the advantages of this high harmonic spectroscopy, that you can cover essentially the full Brillouin zone and also upper bands.
So it's
and everything is ballistic, so you don't have scattering.
So that's
because
the
this
question,
is
not
this is very fast. That's the thing. So you don't have scattering. I mean, you have scattering, but it doesn't kill all coherences before you reach the Brillouin zone.
Okay. So one moment. So this penetration thing for the. Let's wait a moment. That's moving. Sorry.
So thank you for the talk. The valorization thing you do for the band structure calculations, the economic, as I understood. So this is for electrons, but can this be done for photons?
For photons.
For photons, for photonic band structures.
I mean,
probably yes.
In principle, yes.
It's just
I don't
mathematics. So
you are thinking about like some photonic band structure, and then in principle it's just a matter of doing Fourier transform of the band structure.
Okay. So good. Good to know. Because
it is the same.
But I don't know.
Because in photonic band structure you just have like the solutions of the Maxwell equations.
No, it's exactly the same.
And then you will have like.
So but you're thinking of photonic waveguides or something like this, So there you would prepare, let's say, a wave packet in some place, and then you.
Because
it will actually what we do will be the same, because it's essentially just we propagate in Z direction, we propagate in time, but.
Because I remember that these Wannier functions were used they were used to calculate, to simulate or to extract defects, cavities, nanocavities in photonic crystals more easily than if you use. Because you concentrate the Wannier function in the defect, and then you could calculate everything. I remember that.
I mean, if you have like a photonic lattice or an optical lattice, actually, if you have like, then you work out what are the Bloch functions. The Wannier functions are actually like the sides of the optical lattice. In more complex things in which you have crossings or you have multiple bands, it might be some combination of this, but like imagine just a simple optical lattice, like the Wannier functions are just like localized photons.
Okay.
Localized electromagnetic modes, actually, not photons.
Okay, good. Thank you.
Any other question or comment?